OSPF packets. In this video, I am going to talk about the different OSPF packet types and the functionality of each packet. You know that in previous video, we have learned about the OSPF neighborship, and we know that in OSPF neighborship, we are using OSPF hello packet for discovering neighbors, and after the adjacency we are using the hello packets for maintaining the adjacency or neighborship. But in OSPF we have different type of packets. Because of that, we should learn about each of these packets. Here in this table you can see the different OSPF packet types. As you can see, the first packet type is the hello packet, is the OSPF hello, and you know that we are using the hello for discovering neighbors and build adjacencies between them. Okay, but the last four OSPF packet are working for the link state exchange. As you can see, the first or the second type of the OSPF packet is DBD. DBD is the abbreviation of the database, okay, database description. Database description. In some cases, in some references, maybe you see instead of DBD, DD or DBD, both of them are same. I will talk about the function of DBD, but now we know that we have one OSPF packet types with the name of DBD. The next OSPF packet type is the LSR. As you can see, LSR is the abbreviation of the link state request. I will talk about the function of the link state request in this video. After that, you can better understand the functionality of this LSR. And after that, we have the next packet in the OSPF. The name of this packet is the LSU. LSU is abbreviation of the link state update. Okay, you know that when we want to send link state advertisement, actually we are using link state update. In each link state update, we have multiple link state advertisement or LSA. I will talk about the detail of LSU now. After that, we have a link state acknowledgement, okay, or link state ACK. Link state ACK is the abbreviation of the link state, okay, acknowledgement. You know that OSPF should send acknowledgement to when we are receiving, for example, link state update. This means that I have received your update, thank you, that's it. Okay, if we don't send link state acknowledgement, the other side maybe thinks that it should send again the link state update. I will talk about all of these packets, but for now let me to start talking about these four: DBD, LSR, LSU and LSAck in this simple scenario. In this simple scenario, you know that we have R1, R2 and R3, and between them now we have adjacency. Actually, between the router 1, router 2, router 2, router 3 and router 1, router 3, we have neighborship now. Because of that, we are assuming that neighborship was occurred before than our talking. Okay, we are talking about the link state exchange after the neighborship. You know that after neighborship establishment, routers should send to each other the link state updates or link states for example advertisement. Okay, here we are learning about the detail of the link state advertisement and also how the routers are sending this update to each other. You know that in the distance vector protocol, such as the EIGRP, such as the RIP, okay, each router should send its information only to its neighbor. For example, assume that here we are using EIGRP and this is the router 1, this is the router 2, this is the router 3. You know that router 1 or RIP, both of them are same. Assume that here we have a net A. R1 should send net A to the router 2 with its update. For example, this can be the routing protocol of RIP or EIGRP. Let me to use RIP. You know that in RIP we are sending with each update the metric. Metric is hopcount. For example, we are sending metric 1 means router 1 has metric of 0 to the net A, but router 2 has metric of 1. In the RIP we are sending metric with one value more, means you have a distance to this network with the metric of 1. Okay, But the R2, when the R2 sending this update to the router 3, it should change the values in this update. For example, it should send the metric as 2. Means R3, you have metric 2, okay, or distance 2 to the net A. Actually, in the distance vector protocol, as you can see in this example, each router, okay, should send up its connected networks or its routing table to the only directly connected neighbor, and directly connected neighbor, after increasing some values related to the metric, should send this update to other routers. Okay, actually here R1 doesn't send its update to the R3. R1 send its update to R2, and R2 after some change they should send this update to the R3. This means that R3 doesn't receive the R1 update. The R3 is receiving R1 update plus some change. Okay, this is the behavior in the advanced distance vector protocol or distance vector protocols. But in the link state protocol, okay, when R1 is creating one link state, we expect this link state receive to all routers, okay, without any change. In this scenario, as you can see, we have one direct link between the router 1 and router 2 and router 3. Assume that we don't have link between the router 1 and router 3, okay? When the R1 sending its link state to R2, okay, we expect this link state without any change receive in R3. Let me first introduce this scenario. After that, I will talk about the, for example, what is happening when we have one line between the R1 and R3. Here, we can start our talking about the, for example, link state of R1. Assume that R1 now is creating its link state. You know that in the link state link state of R1, we have multiple link state advertisement. For example, in the link state advertisement of R1, R1 says that I am connected to this network or to other information. I will talk about the information of the link state with more detail in future, but let me to say this is the link state of R1. We are trying to sending this link state of R1 without any change to the router 2 and to the router 3. How we can send it? Look at here in the database of R1, actually in the link state database of R1, now we have one link state, and that is the link state of R1. Each link state, okay, has one sequence number. Here we have one sequence number. For example, sequence number is 1, but I will show you the real value of the sequence number. Let me write here the real value. Real value is a hex value, okay, and this is the default, for example, value. We have 1860, okay, and then 11. That's it. This is the first sequence number. The next sequence number is 2, and so on. I will talk about that. Let me, for easier understanding, using the sequence number 1 and the age, and we have one age for an entry. Age means the age of the record. Age of the record when we are creating the link state in the R1 is 0 second, but when after 1 second the age should increment to 1, then 2 second, then 3 second, 4 second, 5 second. Age is incrementing value. Okay, the age is not important for us, but let me to write here, for example, age is 1 second. Okay, this is the entry of the link state of the router 1. We are trying to send this link state to the other routers. How we are sending the link state to the router 2? In the OSPF, okay, we are using the DBD as the first packet for exchanging the information. DBD is the database description. Actually, in the DBD, we don't have the full information. We have only description of our database. For example, this is the DBD, okay, and the R1 sending this DBD to the router 2. What does the function, the usage of the DBD? For example, here we have this information. R1 says to R2 that I have link state of the R1 or our link state, okay. Here we don't have the real information. Actually, here we have only a description. I have link state of R1 with the sequence number of 1. Do you want it? This means that the router 1 now is informing the router 2 about this link state. First, router 2 should verify its link state database. You know that in the link state database of router 2, now we have only link state of the router 2, not link state of router 1. Because of that, R2 understands that it needs this link state, because you know that each router needs all of the link states of other routers for creating the topology. Okay, because of that, after receiving the database description from the R1, R2 should send one link state request. Means I need your link state advertisement. I need your link state. How? With the LSR. This is the LSR. We are sending the LSR or link state request from the R2 contain our request. I want to receive link state of router 1 with the sequence number of 1. Why I want to receive it? Because I don't have it, okay? Or I don't have this version. Because of that, this sequence number. When you are sending link state request from the router 1, the router 1 should send the detail or the link state itself. Because of that, the router 1 is sending one link state update. I will show you. In the link state update, actually we have all of the link states advertisement about the link states of the router 1, and now the R2 has this link states. Because of that, here we will have link state of the router 1, okay, with the sequence 1, okay, and for example age now is for example 5 seconds, okay. After 5 seconds we are receiving it. That's it. Also, you know that OSPF should send one link state acknowledgement. This means that I have received your link state, thank you, please don't send it again. Because of that, again router 2 should send a link state acknowledgement or LSAck, okay. Because of that, now we acknowledge in the router 2 that we have received the for example link state update of router 1, and now the process of receiving this update in the router 2 is finishing. Now you can better understand these terms. DBD, database description, checks for database synchronization between routers. When we are sending the DBD, from the DBD include the link state of R1 with sequence of 1, actually R1 tries to synchronize the database or LSTB between the router 1 and router 2. LSR, link state request a specific link state record from another router, as you can see. LSU, link state update, sends specifically, okay, requested link state request. That's it. Then link state record. LSAck or link state acknowledgement. Link state acknowledgement acknowledge the other packet types. That's it. Now you know that R2 should send this information to the router 3. Now in the database of router 3, we have only the link state of the router 3, for example with sequence number 1, age of 1 second. Okay, when the R2 has new information about one link state, for example link state of the router 1, the R2 should send one DBD to the router 3. Let me to show you here again. The process is repeating. Router 2 send this DBD, okay, to the router 3. I have link state of R1 with the sequence number of 1. Do you want to receive it? Again, router 2 should first verify its database. As you can see here, we don't have this information. Because of that, the router 2 should send a link state request. Okay, this is the link state request received from the router 2, and here we have the request for receiving the link state of router 1, okay, the previously offered link state with the sequence of 1. This is the request of the router 3. Okay, after that, you know that the router 2 should send the detailed information of the link state of R1 with the LSU or link state update, okay, to the router 3. After that, the router 3 should send link state acknowledgement, means I have received this update, please don't send it again. That's it. Now in the router 3 also we have this link state of the router 1 without any change. For example sequence 1, okay, and age is 1 second. As you can see, in this process router 1 sends its link state to the router 2, and router 2 advertise the link state of router 1 without any change to router 3. Actually, all routers have the same link state of the router 1. About the link state of router 2 and router 3, this process is repeating. Now, assume that in router 1 we are adding one link or removing one link or changing the metric or some other things. Okay, assume that here now we are adding one network, for example net A. This is one of the interfaces of the router 1. You know that this is the change in the link state of router 1. The router 1, okay, should increase its sequence number to 2, and after that it should reflect this change into its link state. Now we have the link state of router 1 include this change. Okay, net A, sequence number 2. You know that the router 1 should inform other routers about this change. What is happening? Again, the router 1 is sending the next DBD to the router 2, but in this DBD we have the sequence number of 2. This means that I have link state of router 1, okay, with the sequence number 2. Do you want it? First, router 2 should compare the sequence number of link state R1 with the sequence number of link state R1 in its database. As you can see, it can find that here we have some information, okay, because some new information, some more recent information in the link state of router 1. I don't have this information. Why? Because our sequence number about the LSA of the router 1 is 1. Because of that, again, the router 2 is sending link state of the for example link state request with the link state of request for link state of R1 with the sequence of 2, and then here we have again the next link state update, link state of R2, sequence is 2, okay, and finally link state acknowledgement from the router 2 to the router 1. Link state of the router 1, this is router 1, but the sequence number is 2. That's it. Maybe in some implementation of the OSPF you see that when we have one change, router 1 send DBD and after DBD immediately the LSU, but in normal process, in a standard process, we should send the LSR and then we are receiving LSU. Again, router 2 should advertise link state or a DBD for the link state of R1 with the sequence number of 2. It should receive LSR for this sequence number. Again, we are sending the LSU, and finally we are receiving the link state acknowledgement. And here in the link state table, okay, or LSDB link state database, we will have the new sequence number. This is the process of updating in the OSPF, but only, you know that we are sending the information to another router when the next router is requesting that information from us. Assume that here we have one link between the router 1 and router 3. I'm going to talk about what is happening when we have this link between the router 1 and also router 3. Let me to start from the scratch. I'm going to talk about that what is happening first when router 1 has direct link to the router 2. Let me to start from the scratch. You know that now in the link state database or LSDB of router 1, we have link state of router 1 with the sequence number of 1. You know that the R1 should send the, for example, DBD, it's DBD to the router, for example, 2, and also to the router 3. Let me to show you, we are sending another DBD, okay, to the router 3. Let me to use it here because we will use them. Let me to copy them here, okay. Look at here, R1 is sending another DBD to the router 3. This is the DBD of the R1. Again, here we have link state of R1, and then with the sequence number of 1 means, do you want this sequence number of the link state of R1? And you know that in the LSDB of the router 2 and router 3, we don't have any information about the link state of router 1. Okay, this is the first step. We are sending this link state, this DBD, to the router 2 and router 3. Both of router 2 and router 3, okay, should send us one link state request. For example, from the router 2, we are receiving this link state request for the link state of router 1 with the sequence number 1. And also, we will receive another for example, LSR for the sequence number 1 of the link state of router 1, okay? And then this is the LSU. This is the LSU of the router 3 sending to the router 1. I will show you. After that, you know that router 1 should send link state update to the router 2 and also to the router 3. Let me to show you. This is the link state update LSU. To the router 3 include the link state of router 1 with the sequence number, for example 1. That's it. And after that, you know that the router 2 and router 3 should send their link state acknowledgement or LSAck to the router 1. Also here we have the next link state acknowledgement, LSAck, okay? LSAck to the router 1. Now both of the router 2 and router 3 have this new link state advertisement of the router 1 with the, for example, sequence number 1 with the age of, for example, 5 seconds, okay? And also here in the LSDB of router 3 we have the similar information, link state of router 1, then a sequence number is, for example, 1, and then age is 5 seconds. That's it. This is the information of us related to the link state of router 1. After that, you know that router 2 doesn't know about the router 3's relation with R1, and also router 3 doesn't know about the relation of router 2 with R1. Each one of them is receiving the update first. Because of that, for example, assume that the R2 is receiving the update from the router 1 before than the R3. R2 sends its DBD, okay, to the router 3, means I have the, for example, I have the one link state request for the router 1 with the sequence number of 1. Do you want it? You know that R3 itself has this link state advertisement, okay? Because of that, the R3 doesn't send link state request to the router 2 because router 3 has this update. And now the process is finishing here. Actually, we know that in OSPF with the sequence number and DBD, we can understand that the other neighbor or the, for example, our neighbor needs to receive the link state or does not need. If the router 3 sends us a request, send the request to the router 2 can inform that the router 3 doesn't have this information. But when the router 3 doesn't send the, for example, request, this means that the router 3 has itself the information and we don't need to send the router 3 this information, this link state. This is the process of the link state exchange loop removing, means the link states, okay, should not stuck in one routing loop for all time in the, for example, scenario. When one router doesn't send link state request, we understand that that router has the newer version, newer sequence number, or has the, for example, equal sequence number. We don't need to send it again. That's it. This here you can see the process and the function of the each OSPF packet, such as the DBD, such as the LSR, such as the LSU, and such as the link state acknowledgement. Let me to show you one simple scenario. For example, I am going to talk about the link between router 1 and router 2. What is happening between two routers? Let me to show you what is happening in one simple scenario when we have two routers, R1 and R2, and the process of exchanging link states between them. As you can see, we have one simple scenario. In this simple scenario, I am going to configure one range of IP address, for example, 10.120/24, okay? And after that, we will configure OSPF and we will experience the, for example, link state exchange. Also, let me to configure also one loopback interface, loopback 0 in the router 1. Okay, this is the loopback 0 with the IP address of quad 1/32, and after that we will talk about the link state exchange. Look at here in the router 1. First, we should configure this IP address, interface serial 10 IP address is the 10.121.255.255.255.0, and then no shutdown. This is the router 1 configuration. I will configure the loopback 0 in the next step. Then interface serial 10, again IP address 10.122.255.255.255.0, and then no shutdown. That's it. Now we should enable the OSPF, but before configuring the OSPF, let me enable the Wireshark or sniffing here, because I'm going to show you what is happening about the OSPF. In this capture, we will filter only the OSPF packets. Let me to show you. Here we have only the OSPF packets. Okay, after that, let me start with the configuration. In the R1, we can use a router OSPF1. Okay, assume that router ID is quad 1. Then we are configuring the network. Okay, network 10.121 quad 0. That's it. This is the or area 0. This is the commands that we need, only the simple configuration. As you can see now on this interface, we have the OSPF hello packet. This is normal. In the router 2, here I'm going to configure again router OSPF1, router ID is quad 2, and then network 10.122 quad 0, area 0. What is happening? Look at here. Here you can see the process, and you know that we have configured the OSPF, okay, between the router 1 and 2, route OSPF process ID 1, and also area was configured as quad 0. That's it. This is our configuration. Okay, look at to the capture. In the capture, let me to stop the capture. We have these packets. As you can see, first here we have the OSPF hellos from the router 1 from the 10.121, okay, and then 10.121, 10.121. Now 10.122 means router 2 is sending its hello, and because of that, after this hello we will have neighborship between the router 1 and router 2. Here we have some little detail. I will talk about them, but first let me to review all of the things we have talked about them before. Look at here. After the hello message between the router 1 and router 2, we will have neighborship, and here you can see that we have neighborship between two routers. Also in the router 1, do show IP OSPF neighbor in the router 1, and in the router 2, do show IP OSPF neighbor, we have neighborship. But as you can see here, we have another OSPF packets. The router 2, okay, is sending its DBD. DBD is sending to the in this packet to the 224.0.0.5, the multicast MAC address, the multicast IP address of the OSPF. And as you can see, again the router 1 is sending DBD. Okay, the router 2, router 1. After that, we can see here we are receiving one link state request. For example, router 1 is sending its DBD, and then router 2, okay, is sending its link state request. Okay, let me to show you what is happened here. First, this is the OSPF hello. Okay, OSPF hello. Let me to write here only the hello. Okay, and the hello's destination is 224.0.0.5. Also, we are receiving another hello. Here we have some other details. I will talk about them. Okay, but for now, let me to say that we are sending hello, and also we are receiving hello. The hello is sending to the multicast IP address of the OSPF. Okay, 224.0.0.5. This is the first packet. After that, let me to show you only one way. For example, from R1. R1 sending its DBD to the 224.0.0.5, okay, and after that we are receiving the link state request again from the 10.122. This is the link state request, LSR, but this is a two-way process, means the router 2 also should send its DBD, and after that it should receive its link state request from the router 1. Okay, this is the link state request, and then as you can see, router 1 is sending the link state update. Let me to show you. Here we have one link state update, LSU. Okay, LSU again to the 224.0.0.5. And then let me to show you what is happening. After link state update, we are receiving the link state acknowledgement again. And you can see the process is completing. LSAck, this is the LSAck. or link state update 224.0.0.5. You know that the source IP of the OLAF packets is the unicast IP address of the outgoing interface. For example, LSAck has this source IP 10.122, and then this LSU has this source IP 10.121. Okay, let me to show you. Also, the link state request receiving from the router 2 has the 10.122 as the source IP, and here we have 10.121. That's it. This is the process. Okay, let me to start again the capture, because we stopped the capture. Here we should stop and then start. Okay, and then start. I will talk about the detail of this, but for now let me to show you first the database. In the database of router 2 show IP OSPF database, we have this information. You will learn about all of the detail of this information, but for now let me to say that here we have one link state database received from one link state advertisement from the router 1, advertiser router is router 1, and another link state from the router 2, from ourselves. Okay, because of that, this is the information that we have received from the router 1. This sequence number, okay, is the sequence number of this link state request, this link state advertisement, and also this is the age, 264 seconds. Don't worry about the detail, okay? Only let me to copy them because this is helpful. Here in the router 2, okay, we have link state of the router 1, okay, and here we have this age, this is the age, okay, and then this is the for example sequence number. You will understand why I am copying these values here, because I'm going to show you what is happening when we are receiving in the new update. In the R1, I'm going to add the loopback 0 interface. Loopback 0 IP address is the quad 1, then quad 255. Then let me to send this route to the router 2 with the router OSPF 1, then network quad 1, okay, quad 0, area 0. As you can see, I am trying to send this information to the router 2. Okay, in the router 2, if you check the database, show IP OSPF database, now you can see that we have one new sequence number with the age of 7. 7 means 0, 1, 2, 3, 4, 5, 6, 7. That's it. Means now we have received this update 7 seconds before. As you can see, the sequence number increased. Why? Because router 1, okay, sent the new link state with one number, okay, higher than the previous sequence number. Here you can see also the process in the capture. Let me to show you what is happened. OSPF. First, we can see the hellos between the router 1 and router 2. 10.121 sent 1 dB, one link state update. Look at here, one link state update. Here in the link state update, we have the new link state, okay, include the quad 1. As you can see here, we didn't send the DBD. This means that in some cases, in some implementation, when we have one change, we don't need to, for example, send DBD or some other things. We can send directly the link state update, and after that we will receive link state acknowledgement. Don't worry about the detail of this process. This is a little beyond the scope of this course, but let me to say that in some cases maybe you encounter with directly sending link state update and link state acknowledgement that we are receiving. Actually, OSPF with link state acknowledgement try to acknowledge its packets. Means the OSPF is a reliable protocol, but the reliability of protocol is not for example, working with the TCP, EIGRP and OSPF, both of them have some specific packets for sending acknowledgement. In EIGRP, we are using EIGRP ACK. In the OSPF, we are using LSAck or link state ACK for acknowledging the, for example, LSU, LSR, and also DBD. Don't forget that we don't send link state acknowledgement to the hello. Actually, hello is an unreliable packet, okay, of OSPF. And also we don't send link state acknowledgement to the LSAck. This is so important. Okay, until now we have learned about the functionality of the OSPF packet types: hello, DBD, LSR, LSU, and also LSAck. Now we can talk about the OSPF state. In OSPF, we have one engine, we call it the FSM or Finite State Machine. Finite state machine function is, for example, keeping the states of each neighbor. After that, we can use these states for understanding our status related to that neighbor. For example, if we are stocking in the Exstart state, okay, you know that this may be result of the MTU mismatch between the router 1 and router 2. Or if we reach to the full state, this means that we don't have any problem and our link state exchange process is completed. Because of that, we should know about the different states in the, for example, OSPF. Let me to talk about this OSPF states. Assume that here we have router 1 and router 2. Okay, we have configured these two router with the OSPF, and here you can see the process that is occurring between these two routers. In OSPF, we have these states: down state, initiate state, two-way, Exstart, exchange, loading, and full. Okay, let me to explain the function of each state, why we are residing in down state, initiate state, and so on. Okay, the first thing that I'm going to talk about that is the first three steps, or the first three states, okay, are related to the adjacencies or neighborship. After that, we are, for example, passing, okay, we are completing the link state exchange. As you can see, down, initialize, and two-way are states of the establishing neighbor adjacency. Means if two routers establish neighbor adjacency between them, okay, actually they are reaching only to the two-way state, okay. But if these two routers are exchanging the link states with each other, they reach to the full state, and the full state is the means that we have complete neighborship, and also we have completed the link state advertisement. For example, here in the router 1, if you want, you can see the full state: show IP OSPF neighbor. Look at here, we have the state of full. What does the meaning of full? This means that we have neighborship with router 2, and also we exchanged before the link states with this router. Means everything is working correctly. Now let me to talk about the detail of these states. Here with this picture, you can easily understand everything related to the OSPF state. First, when we don't have any, for example, configuration, or we have configured the OSPF but we didn't receive any hello packets, we are residing in the down state. Actually, down means the initial state of a neighbor relationship. It indicates that the router has not received any OSPF hello packet from the router 2. Assume that, let me to show you on the router 1, okay, here, let me to show you here. In the router 1, we have configured this command, no router OSPF 1. Now we don't have OSPF configuration, no router OSPF 1, okay. And also in the router 2 also we don't have any OSPF configuration, no router OSPF 1. Okay, without any configuration, you don't have the OSPF at all. Here we don't reside in the down state. Actually, we don't have OSPF at all. When you are configuring the OSPF in the router 1, router OSPF 1, okay, as you can see, now we have configured the OSPF 1. Router is selecting its router ID, and then we are configuring network 10.1.2.1 quad 0, then area quad 0. Means we are sending OSPF hello, okay, from the router 1 to router 2. That's it, okay. Actually, you know that now we are residing in the down state. Why? Because we are sending the OSPF hello, okay, to the other side. But as you know, in the router 2, we don't have any configuration of the OSPF. Actually, we are residing in the down state without any interaction with the router 2. But when you are configuring the, for example, OSPF in the router 2, okay, router 2 is receiving, for example, this hello, okay. Assume that now we have configuration of the OSPF in the router 2, okay, and then the router 2 is receiving this hello. Now we are in the router 2 residing in the init state. What is the init state? Init is the abbreviation of the initiation, okay, init. a state in which a hello packet has been received from another router, okay, but bidirectional communication has not been established. This means that the router 2 is receiving the hello, okay, from the router 1 that is residing in the down state. Here now we are in the init state in the router 2, but because router 2 doesn't send any hello packet to the router 1, this means that the router 1 doesn't know anything about the router 2. Okay, you know that in the hello we have one field, we call it active neighbors. In the active neighbors, because router 1 doesn't know about the router 2, we don't have any information. Actually here in the active neighbor we have null information, means empty information. And here also in the hello, you know that R1 should send its RID of the for example router 1 is 192.168.1.1. okay, this is the RID we have configured in this picture. Let me to configure it here. RID is 192.168.1.1. okay, let me to show you in our scenario router ID 192.168.1.1. let me to show you also the capture. This is our capture of this scenario. Here now we have some hello packets from the router 1. Here you can see in the OSPF header that the source OSPF router means router ID is 192.168.1.1, but because the router 2 doesn't have the configuration of the OSPF, okay, actually we are residing in the down state. But when the OSPF is enabling with this, when the router 2 is enabling with the OSPF, router 2 goes to the init state. And then you know that the router 2 should send its hello to the router 1. Let me to show you. This is the hello of the router 1 received from the router 2. You know that the destination IP of each hello is 224.0.0.5. okay, also here we have the same destination IP again, 224.0.0.5. okay. After that, the router 2 should send its hello packets. This is the hello of the router 2. Destination is again 224.0.0.5. And this is the, for example, OSPF hello. Here, you know that the source IP of the OSPF hello is the IP address of the outgoing interface. Okay, for example, here we have 10.122. That's it. And then in the active neighbors, you know that in the active neighbors, in the received hello, we have null, means we don't have any neighbor. But here in the active neighbors, the router 2 is using the router ID of router 1. When the router 1 is receiving this hello, it can understand that the router 2 received the hello of the router 1. Because of that, the router 2 is sending the router ID of R1 in this hello to the router 1. This means that router 1 now ensure its hello received by router 2, and router 2 sends back the hello, okay, with the router ID of router 1. Here we have in the active neighbors router ID of router 1, 192.168.1.1, okay. And actually the router 1 now ensure that the router 2 can receive its hello. Because of that, the router 1, okay, is going to the two-way state, the next state, okay, two-way. And after that, in the next hello that we are sending to the, for example, router 2, here in the active neighbors, as you can see, the router 1 is using the RID of the, in the active neighbors, we are using the RID of the router 2. Also, because of that, router 2 can understand that router 1 received its hello, and now in both sides, we have in the two-way. Actually, don't think that this process is a one-way process. In most cases, you can see this process occurring in, for example, similar time down, initialize, and then two-way, okay? Both of router 1 and router 2 should pass these three states. Look at here. Again, we can review. R1 doesn't receive any hello from the router 2, and R2 doesn't receive any hello from the router 1. Both of them are residing in down state. R1 sending its hello, and now the R2 is initiate state, residing in initiate state, and this is the hello with the active neighbors field of null with for example, information of null. RID is 192.168.1.1. Then we are receiving the hello from the router 2. In the active neighbors, we have 192.168.1.1, means I have received your hello, router 1, okay, and this is my router ID. Then the next hello, that router 1 now is residing in the two-way state. The next hello received from the router 1 include active neighbor neighbors 192.168.1.1, 192.168.2.2, and the RID of router 1. And this means that now these two routers are reaching to the two-way state. Let me to show you until here, okay, in the capture file. I'm going to show you until the two-way state, okay. Here in our configuration, we should configure also the router 2. Router OSPF 1, okay, then router ID 192.168, for example 2.2, and after that network 10.1.2.2 quad 10.1.2.2 quad 0, again area quad 0. That's it, okay. Let me to show you what is happening in the capture file. This is our capture file, and in the capture file you can see the process. Look at here, when we had only the hellos from the router 1, okay, this is the router 1 hello, this is the information in the OSPF hello packet. You have learned about them: version, message type, packet length, source OSPF router means router ID, at area ID, checksum. This is for for ensuring that this packet is noise free. Authentication type, authentication data. After that, OSPF hello packet network mask. This is the mask of the outgoing interface, hello interval. And then here, as you can see, we don't have any active neighbors, means active neighbors include null information. After that, the hello received from the router 2. Okay, this is the hello from the router 2. And here we have this information. This is the hello from received from the router 2 before receiving the hello from the router 1, because we have configured the OSPF, for example, in the router 2 after the previous hello receiving. And then hello from the router 1. Okay, this is the hello from the router 1. You can see that active neighbors now is 192.168.2.2. Why? Because router 2 sends its hello, and the router 1 sends the active neighbor 192.168.2.2. And then here in the next hello, we have the active neighbor of 192.168.1.1. Now these two routers are reaching to the two-way state. Okay, down, initialize two-way. Before going to the next steps, let me to say that in some special type of the OSPF neighborship, we call it the static neighborship. Here we have one state between the down and initialize. We call it attempt state. Okay, attempt, I will talk about the attempt, but let me to say that this is beyond the scope of NRC, but I will explain it for you. After that, look at here, down, initialize two-way. This is the normal process. Attempt only is occurring when we are using the static OSPF neighborship. After that, we should go to the next step, Exstart, exchange and loading. These steps are working for the link state exchange, not neighborship. Now we have neighborship. Here in the first step, you know that we are exchanging first the DBD and then link state request and then link state update and finally link state acknowledgement. Here we have a process, we call it the DR election. DR election or designated router election is one step, okay? You will learn about it in the next video. I'm not going to talk about the DR election now. You will learn about the detail of what is the DR, BDR and some other things in the next video. But let me to start from here, from the Exstart state. The DR election is running in the last part of the neighborship. Because of that, don't worry about the DR election now. Here, the first step after the two-way, you know that now until here we have received to the two-way state. Okay, this is the two-way state, or also in two sides we have two-way state, means we have neighborship. Okay, after that, the next step is Exstart. Exstart is the abbreviation of the exchange start, means we are starting the exchange of the link states advertisement. Okay, here we have some features. For example, one of the routers should select it as the DR, as the master, another is a slave. The detail of these functions is beyond the scope of NRC, but let me to say that master is the router with the higher router ID and the slave is the router with the lower router ID. For example, if the router 2 has higher router ID, the router 2 will be master and router 1 will be a slave. But according to the master slave, we can identify which router should initiate the sending the link states and which router should follow the link state exchange. The detail is not important, but let me to say that in the Exstart state, okay, this is the first state in forming an adjacency. Routers, after forming adjacency, routers identify which router will be the master or a slave for the link state database synchronization. But let me to say that in this state also we have another function, and that is the MTU checking. You know that if we have the MTU mismatch between two interface are, for example, two routers are stacking in the Exstart state. The reason is that in this state we are checking the MTU mismatch between two routers. Okay, now you can better understand it. After that, as you can see, in the exchange state we are sending the DBDs, DBD of R1, DBD of R2. Okay, this is the exchange. And finally, in the loading, we are sending link start, link state request, link state update, and link state acknowledgement. This is the loading process. And after the exchanging these three packets, finally we will reach to the full state. Let me to say that in exchange, this is the state during which routers are exchanging link state by using DBD packets. And the loading, this is a state in which LSR packets are sent to the neighbor asking for the more recent LSAs that have been discovered but not received in the exchange state. And after that, a full means a state in which neighbors' routers are fully adjacent. And finally, in this state, we can ensure that we have all of the recent information that we expect from our neighbor. This is the overall process. Now you can easily understand why in the show IP OSPF, okay, show IP OSPF neighbors, here we have the state of full. Full means we have full adjacency with our neighbor, means we have adjacency and also we have received all information from our neighbor. This is the first thing. After that, let me to say that if you want, you can see this overall process. For example, you can use one of the debug commands, debug IP OSPF adjacency for example, verifying these states. Let me to write here. This is the command useful for debugging and also troubleshooting of the OSPF adjacency. Debug IP, okay, OSPF, then ADJ. That's it, means adjacency. Here in the router 1, let me to enable it. This is the router 1. Debug IP OSPF adjacency. That's it. And then let me to, for example, remove the OSPF 1. No router OSPF 1. Now we don't have OSPF. Okay. And then I'm going to enable OSPF. What is happening? Router OSPF 1 network. Okay, 10.1.2, for example, if you want, you can configure the router ID first. Router ID is 192.168.1.1 in this example, and then network 10.1.2.1 quad 0, and then area again quad 0. Look at here. Here we will see the different state that for example, we have in the OSPF. Let me to undebug first, do undebug all. Here we have this information, two-way communication. Now a state is two-way. From down we went to the for example, two-way, and after that here we are sending DBD and also we are receiving DBD. Okay, and this is the Exstart, as I mentioned before. And as you can see, this router is the slave router. We are the slave because the router 2 has higher router ID 192.168.2.2. And after that, as you can see, now we are starting the exchange state. This is the exchange. And after that, here you can see that we are working in the loading state and finally to full state. Here we can see two-way, Exstart, exchange, loading, and also full. In some other debug command, maybe you see, for example, the name of initialize or some other things. Okay, all of these states are important. We should know about the function of each state. For example, if we see that we are residing in the Exstart state, means we have a problem related to the, for example, MTU or some other things. Now let me to talk about the next state, the attempt state. You know that in some cases we are experiencing the attempt state in the OSPF, and for example, in the non-broadcast multi-access or NBMA network, we don't have the option of passing the broadcast and multicast packets. You know that in FrameRelay, as this is the one of the non-broadcast multi-access networks, and we cannot send broadcast packet or multicast packet from this network. Actually, here when you are enabling OSPF on the interface of router 1 and also on the interface of router 2, the broadcast and multicast packet cannot send from the R1 to R2 or R2 to the R1. Because of that, we cannot use the dynamic neighborship feature of the OSPF. Why? Because the OSPF dynamic neighborship is, for example, occurring with the OSPF multicast hello packet, and because here we are using the OSPF, we are using the FrameRelay network, we cannot use the OSPF multicast packets. We should use the static neighborship. For a static neighborship, besides other configuration in the OSPF, we need one new command. This is beyond the scope of this class. Only for your information, you should use neighbor then neighbor IP. For example, neighbor 10.122, and after that you will send one unicast hello instead of the multicast hello to the other side. I will show you. Until now, we have learned about the dynamic neighborship. Here we are experiencing the static neighborship, and after that the attempt state. Don't forget that this is beyond the scope of this class. For example, here I have configured the R1 and R2 with the FrameRelay configuration. Let me to show you. If you want, you can do exactly with the same configuration, but you know that this is beyond the scope of this class. Look at here. First, on the interface serial 10, we should change the encapsulation to FrameRelay without IP addressing, and then we should have one interface serial 10.1. This is multi-point FrameRelay interface or sub interface. The IP address is 10.1.255.255.255.0, and then I have configured FrameRelay map IP 10.122.100.02. Also in the router 2, I have configured this command. Again, you know that this is beyond the scope of the CCNA class, but the NRC class. Okay, here as you can see, interface serial 10, no IP address, encapsulation FrameRelay. Then interface serial 10.1, IP address is 10.122.255.255.255.0, and the FrameRelay map I 10.121.200.01. Also in the FrameRelay switch, I have configured this value, the port 1 with the DLCI of the 100.02 connected to port 2 with the DLCI of 200.01. If you want, you can copy all of this configuration, but if you want only, you can view this part of the video. Now let me to configure the OSPF in the router 1. Okay, conft router OSPF 1, then network 10.121 quad 0, area for example quad 0, and also in the router 2, router OSPF 1, network 10.122 quad 0, area again quad 0. As you can see, now we don't have any neighborship. Do show IP OSPF neighbor can show us that we don't have any neighborship. Why? Because in the multicast network, in the non-broadcast multi-access network, in the FrameRelay network, we cannot send the multicast hello packet. Okay, because of that we will not have the neighborship. Okay, let me to show you the neighbor command. Neighbor 10.122, and then here neighbor 10.121 in the router 2 and router 1. After that, on the router 1, let me to show you what is happening. Show IP OSPF neighbor. Now we are residing in the attempt state. You know that in the non-broadcast multi-access, we should go from down to the attempt. Also, let me to say that in these networks, in the non-broadcast multi-access networks, the default value of the hello interval and dead interval, okay, is different with the default value of the hello interval and dead interval in the other networks, such as the point-to-point networks or the broadcast multi-access networks. For example, here the hello is for example 30 seconds and dead interval is 120 seconds. You know that by default in OSPF we are using hello interval of 10 seconds and dead interval of 40 seconds, 10 and 40, but here we have 3 times. Hello 30 seconds, dead is 120 seconds. Look at here. Until now we don't have any neighborship. After some second we have neighborship. Show IP OSPF interface serial 10.1 can show us that the hello time, the default hello time is 30 seconds and the default dead time is 120 seconds. If you want, you can capture this link, okay, but when you are capturing, you should use a start capture, then selecting the encapsulation frame lay, and then okay. After that, start Wireshark. Now here we will see the OSPF hello packets. You know that in each 30 seconds you can see one OSPF hello packet. Maybe because of that you should wait more than the normal OSPF process. Because of that I will show you, but because of that let me to say that in some cases, okay, in OSPF we have attempt, but in most cases in the broadcast multi-access networks we are going from down to initialize, two-way, Exstart, exchange, loading, and full. And you know that some of these states are unstable states, such as the init, such as the Exstart, such as the attempt, such as the exchange or loading. Means we don't wait on these states, we are passing these states. But stable states include the two-way, down, and also the full state. Okay, and here you can see the changing state direction. Okay, let me to show you the capture file. In the capture file, as you can see, we have the OSPF packets, and also in the show IP OSPF neighborship I will show you that we have neighborship, show IP OSPF neighbor. Yes, we have neighborship with the router 2. This is the OSPF or static neighborship in the OSPF, but this is beyond the scope of this class. Actually, attempt is a state that is relevant to the non-broadcast multi-access or NBMA network that do not support broadcast and that require explicit neighbor configuration. This state indicates that no recent information has been received, but the router is still attempting the communication. In this video, we have learned about the OSPF states. In the next video, I'm going to talk about the DR means designated router, and also backup. DR means backup, BDR, and also some other notation related to the OSPF states. Because of that, it is important to verifying all of the information in this video. After that, in the next video, in the DR BDR video, we can learn more than this about the states in the OSPF.